Hello everyone, in this video you'll be implementing a facial expression recognition model in Keras using a large pre-trained model called ResNet50. Last time we have learned how to train a model for facial expression recognition. This time I have trained the model with the following data as shown in table 1. So table 1 shows the total data statistics. So for sad emotion category we've got 1247 face images. And for neutral emotion category, we've got 1233 examples. For happy emotion, we've got 1774 facial images. For evaluation, the test set should not contain the examples in train set. It is because we are going to deploy the model on examples that the model has not seen earlier. That is why the performance measure evaluated on train set cannot represent how well the trained model is going to perform on real-world data. Thus, we have split the total data into train and test sets into 80% and 20% respectively. And this figure shows the training process of the CNN model. And you can see that the training loss, this represents the training loss, and this one represents the validation loss, which is computed on the validation data. And as you can see, the training loss is decreasing over the epochs, and I have copied these loss values to my Excel file to plot on a graph. So if I show you my Excel file, I have written down the values, train loss values, and validation loss values for the corresponding epochs. And if you drag them like this, and you can see a graph of these loss values for 50 epochs by clicking this chart. So going back to the slide, you can see the graph of train loss, and the train loss fluctuates over the epochs, and it represents how close the learned feature representation is to the actual label. In this case, the corresponding emotion for the input facial expression. So, in a nutshell, the smaller the loss value, the better the model performs. In fact, that is half true because there is a problem of overfitting. So, this graph shows the comparison of graphs for train. The blue graph is the represents train loss, and this with orange color it represents the fluctuations of validation losses. So as we can see, since 40 epochs, the train loss decreases where the validation loss starts to increase. So this phenomenon in which the model performs well on trained data because the loss is minimizing, but the test data, because the loss gets greater, it is called overfitting. So if the trained model performs well on the trained data, but on the validation data, but poor on the validation data, it is called overfitting. So we should use validation loss for guidance to save the weights for evaluating our final model, because we are going to evaluate our model on the examples that we haven't seen earlier. So note that the final evaluation also should be split from the final test set due to data leakage. So what data leakage means is that the model learns about clues that it cannot know in the real world. So even if the validation data is used for evaluating purpose, anyhow it involves in the process of training the model. So for our final evaluation, the test set should be split from the validation set. So we need to split the total data into train set, validation set, and test set. That is, we train the model by minimizing the loss computed on the validation data and use that saved weights, the best weights, to evaluate the model performance on the test data. So now we'll split the total data into train and test sets into 80% and 20%. Then we'll further split the train set into train and validation sets into 80% and 20%. You'll learn how to save the best weights and load them for final evaluation using Keras. This time we are not going to define the convolutional neural network CNN by ourselves, but use ResNet50, which is a large pre-trained model. In the following video, I'm going to describe more about ResNet50, large pre-trained models, and data augmentation for generalization. So let's go to the tutorial. So I assume that you guys already know about how to use Google Colab because I have uploaded a video earlier, and this time let's create the file called so right click here and on your mouse and go to more option and go to Google Collaboratory, and it'll create a workspace for us, and let's name it as ResNet50 test. Hit enter. And if you go to my GitHub link, I have uploaded the code for earlier example, and I have already uploaded the ResNet50 version, and you can upload it to Google Colab and run it directly. However, I'm going to give you step-by-step explanation as well. So let's copy this line to upload to load the data, and if you let's wait a sec while it mounts. So we do drive the mount to use the to access the data saved in this Google Drive. So just hit allow, and if you go to my drive in dataset folder, double click in FVR folder. I've got go to FVR folder. I've got happy directory, neutral directory, sad directory, and I have downloaded the FVR dataset from Kaggle. And if you go into the dataset, we have train and test set split, and I have used the examples in test set because the more data, the more time takes. So for the time sake, because I'm showing you only just an example, I use test set. So if you go into test set, I have uploaded happy neutral set folder, and if you go into happy folder, we have 1774 examples, and for neutral emotion, we've got 1233 facial images. So let's go back, and you can upload it to Google Drive, and I have already uploaded. And let's go to our workspace and click this plus icon. And if you have run this command, drive mount, you'll see drive folder here, and click this arrow and click this my drive and go to my dataset, and we have F here, and let's copy this directory, copy path, and root R, Control V, and to let's run it. Let's close this, and let's get emotions os the list directory root, and it is going to return us the files, the directories in this root folder. And to use OS library, we need to import this import OS, shift enter. So we see happy, sad, neutral. So we need to declare data images and images list and labels list, and we are going to save the total data, map the images to the corresponding label. So for emotion, in emotions, if you print emotion, we have the corresponding directories, and let's fetch the items, and the full path is going to be full path full path os the path that join root and emotion, and if we os that list directory full path, let's print items. So we see the image file names for the corresponding emotion. So for each item, the item path is going to be, we have the directory path, which is full path, and the item path is going to be os the path that join. It'll be root, root, comma, and here emotion, comma, and final image file name, item. So let's print item path to check whether it's correct. So we have the full path name of the image path. So you can see the images for neutral. If you go further down, we've got only neutral, and let's go up. Maybe up here you can see images for sad. So we need to map these image files to the corresponding label. So first thing, we need to convert the files into a vector. So let's refer to the code I've already uploaded. So this time we are going to use API from this ape image library. So if we go up, the image library is in Keras preprocessing. So copy this and code paste. So Control plus C you can copy, and Control V you can paste it here. And let's do image. Go here again. So to load the image, vector image, paste vector image load image. So in this case, this is item cost, and set the target size to 224 by 224 because the ResNet50 only can receive input shape of 224 by 224 because it is a pre-trained model and we cannot change the input shape. The input shape is already set to 224 by 224. So let's check the shape of the loaded image vector image shape. It's not defined. We need to hit shift enter. So shift enter this cell and hit enter again. We cannot call shape because I guess it's not in array format. So we need to convert it to array image, vector image. Copy the line and paste. Vector image is image to array. And so you can see the shape is 224 by 224 by 3. And we need normalization. So you can use preprocessed input from the API that's provided in TensorFlow.Keras.Applications.ResNet50. Let's copy this line and paste it up here and shift enter again, and vector image preprocess input vector image. So what this preprocess input does is that it tries to normalize. ResNet50 use their normalization technique, which calculates the mean values of RGB. And if we look at the values vector image, let's check the values for this sample image and assert first. So we have 43, these values, and if we do preprocess input on this vector image, let's check the value again. So the value is going to they are normalized. So you can just simply think that you need to call this because ResNet50 use their technique called normalization. Um, so next, we need to map add this vector image to our images list and vector image and labels the append um, for these items it corresponds to this emotion, so let's add this emotion. And once adding all these images are finished, then it loops back to here and fetches another emotion, say it'll be sad, and it'll fetch all the items in the sad directory and fetch all the items and add all the images corresponding to sad emotion, and the labels add them to their corresponding emotion is sad. And once this loop finishes, it goes back to here and it'll gonna fetch neutral emotion, and the full path is the loop path, and then the emotion, and fetch all the items in the neutral directory and add them to images list, and then the add match with map with the neutral emotion for the for these images. So we are going to convert the images to array. Remember that to train the model, it only arrays are allowed for to compute. So images and labels, MP. Um, actually, we'll call categories. So let's check images shape first. Images. We need to define numpy array. Import numpy as MP. Takes a bit of time. Name MP not defined. Shift enter again. And if you remember from last time, we need to do one-hot encoding for the labels. And if you let's go here, the function name is called as doCategorical, and it's in keras.utils. Copy this, go back here, and paste here, and shift enter again. And you can see the total data is 42 and 54 examples, and you can check it here. Emotions. If we let's go up, and happy items length will be os.list directory, os.path.join in root, happy, and sad items will be copy this, paste, change this to sad, and copy, and neutral items, they are in root and neutral path. So total length, total data is length of happy items plus length of sad items plus length of neutral items. So let's print length total data. So 42, 54. And if we go down, 42, 54. So we can assure ourselves that they are correct. The command is correct. And let's convert these labels to categorical. Labels. Then is if you print labels, let's because I don't want to rerun every time fetching this data, so let's put this down here. So something wrong here. Actually, in if we let's go up. If we call labels, it is not. It is in literal. I mean it's in string characters. So it's saying that it is not int. It is not in number format. So this compiler cannot compute understand it. So going up, because we had if we call emotions, so we called emotions here by calling os.list directory of loop folder. We have happy, sad, neutral, and if we call it again here, we can see happy, sad, neutral, and let's sort it to sorted emotions, and it's gonna sort them in alphabetical order, and then you'll match. If you call emotions the index of happy, I index and call index, print emotions and print index. Happy at 0 index, and for neutral it is in the second index. And the note that the index starts from 0. So if we pass set argument, then it's gonna return number 2 because it is at index 2. 0, 1, 2. So it's at index 2. So instead of these characters, we are going to index. We are going to pass index as an argument by emotions the index returning the index of the corresponding emotion. So index here. So let's run this cell again. Here's spelling mistake. Index, the index of emotion. So once it's all run, if we print these labels, they are converted to 000. And if we and from labels maybe 2000 to 2200 to 2100, we can see one for the label value. So if we do categorical, then they are one hot encoded. So the if we go up, the sad emotion is converted to 1. So the position where the sad indicates is marked as 1, but the rest to set to 0. And the same for what was it? Was it happy emotion at index 0? So the index that indicates happy emotion, which is 0, is marked as 1, but the rest will set to 0. So this is one-hot encoding. So once the labels are one-hot encoded, we are led to pass this into our model. To train our model, we need to split them into train, test. So let's do train set, train x, test. Let's first split these images labels into train set and test the set. Train x, test x, train y, test y. So x represents the images and the y represents the corresponding labels. From sklearn the model selection, import train test split, train test split. Let's split it into 80%, 20%. So let's pass images and labels, and the test size is going to be 0.2. That we are going to use 20% of the images, and let's set the random state to 7. Then it's gonna shuffle them to the with the same seed, and then we'll further split this train set into train and validation sets. So train x, validation x, train y, validation y. Copy this line. This time for the x value we pass train x, and for labels we pass train y. So check train x the shape, validation x the shape, test x the shape, and train y the shape, validation y the shape, test y the shape, shift enter again. So we have train x shape 2722 by 224 by 3, validation x of shape 681 by 224 by 224 by 3, and the corresponding labels 2722 by 3, 680 by 3, and we've got test sets of 851 examples. So this time what we are left with to feed this data into our model. So referring to the code that I have already made this time, we are going to use ResNet50 so that we don't have to define the model. So if you remember, last time we have defined the model by adding convolutional layer, ReLU, max pooling, and how you stack these layers, the model performance can increase or decrease. However, this process highly depends on the empirical trial and errors. So rather than you create your own model, it is always a better choice to use a pre-trained model. And this pre-trained model is a model that is already defined with deep layers that have been tested on large scale dataset for good performance, and they usually have a good generalization, which means that they can be used to be for your domain data. So let's use ResNet50 and copy this line and go to the workspace and paste. Base model is assigned with ResNet50 and define the input shape at 224 by 224 by 3. And let's go back to the code, and we need to call ResNet50. And I guess if we go to this workspace, I have already defined the ResNet50 somewhere up here. See here from TensorFlow, the Keras.applications.resonate50 import resonate50. Let's go down, and we're gonna freeze some layers. So actually you can copy all these lines, and I'm gonna explain them briefly. So let's go here and paste, and let's go to the code again, copy this line and go to collab, and down plus code and paste it, cancel, paste it here. So once you assign ResNet50, then we need to freeze the layers, because we are not going to train all the layers. Let's go plus code and let's copy this and paste it here, and let's see module the summary. So it shows the layers that in which this ResNet50 is composed of. Let's go up. Let's see from the bottom. So input 224 by 224 by 3, and convolution padding, convolution batch normalization, activation, zero padding, max pooling, convolution batch normalization, activation, convolution, and you can see so many layers, so many convolution layers with followed by regularizations, activations, and this architecture has been tested on ImageNet data and trained on ImageNet data and proved to be performing well. So, however, because the trained dataset is different from our domain dataset, we need to retrain these layers, but we are not going to retrain all these layers. We are going to train some of the layers. So from the top layer, from this top layer to the 26th layer, we are going to train only some of the top layers. So first we gotta freeze all the layers, which means we are not going to train the weights of the layers, and we'll fetch this average pooling layer. So you can see that here's average pooling layer. It has 248 units, and we fetch this and we downsample it to 3 dimensions. Remember, the final fully connected layer must have the number of units same to the number of categories. So in this case, we have happy, neutral, and sad emotion categories. So we've got 3 emotion categories. So we need to set the number of units to 3, and we are going to train from the 26th layer on, from the top layer. So set it to true, layer the trainable to true. So to save the best model, we are going to save it in the saved models directory, model weights.h5. So let's go to the Google Drive and My Drive, and let's create a folder called new folder, saved models. Create. So currently, if you go in here by double clicking, it is empty currently. And if you train the model, and once it goes through one epoch, then it's gonna save this model weight. And let's define the checkpoint. And model, you can call model checkpoint. And it's gonna save the model weights in model save path. And remember, we need to guide the loss to the minimum. We need to save the weights that have the minimum validation loss. So we are going to, this means that monitor is set to validation loss and mode mean. So we are using this validation loss as our guidance, as our criteria to find the mean value. And we are going to save weights and then save only the best weights whenever the best weights are found. So the model, let's input is going to be base model's inputs, and the output is going to be the X, which is, you see here, which is downsampled as dense to 3. So if you compile, this compile is same as earlier example. We will use categorical entropy for loss function, and this loss function is a formula that calculates this validation loss, and there are many other loss functions, and your model performance depends on this loss function. And if you go into advanced deep learning courses, then you can learn about many other loss functions, some custom functions, and as a researcher, I often try to define my custom losses um, to have superior performance compared to existing baseline models. But most cases, for your application, categorical cross entropy loss is enough. And optimizer Adam is an algorithm that does that runs the weights and metrics. We'll use the accuracy, so it's gonna show the accuracy um, for the training process, and it starts the training with train X and train Y for the train data, and the validation data, you'll use validation X, validation Y. You pass the validation data to this validation data parameter, and this time we set the epochs 10, and it is enough 10 epochs to have good performance because it has dim layers, which is powerful in recognizing objects, and batch size set to 32 callbacks pass model checkpoint callback. So this model checkpoint callback is defined here. So I guess we have to call this API stance model checkpoint. So let's if we go up, let's close this code from Keras the layers importance and model checkpoint. I cannot remember where it's defined. Model checkpoint. It's in TensorFlow, the Keras the callbacks, and copy, paste it here, and model. I guess I remember it's from Keras the models import model, and I think we are done. So shift enter and shift enter. Incomplete. So we forgot this closing parenthesis. Right, add right parenthesis. Shift enter, and the training process starts. So let's see the training process, and once the training is finished, we can calculate the accuracy with model.evaluate on the test data. So this model.load weights loads the saved model weights, and let's compare without this loading weights accuracy, and then let's check the accuracy with loading these weights. Actually, I forgot to change the runtime type. So to accelerate this training process, you need to go to runtime and change the runtime type to T4 GPU. Click OK, save, and because the runtime is changed, we need to rerun. So let's go up and shift enter. I have just realized that the slow training process was because of because we were not using GPU. So let's relearn all these cells. And let's wait a sec. So you see, once we have changed the runtime to GPU, the training process is a lot faster. So you can see what the role of GPU. So using GPU, you can have faster training. So I don't think it's gonna take too much time. So let's wait a sec because it's 10 epochs. Unfortunately, my Google Colab has crashed, so I couldn't run with that much data. So in my Google Drive, I have removed the neutral emotion, and or you can, if you crash as well, then you can remove the neutral emotion directory or some of the examples. Maybe use half neutral images, and going back to the workspace. So remove all the unnecessary commands, but the commands that are used to run this code, and the only things that you need to change is the number of units of the final fully connected layer to 2, because now there are 2 categories of sad and happy. Here, sad and happy emotions in the FPL dataset, and change the loss function to binary cross entropy. So if you're doing um, task, solving a task for binary classification, then you can use loss function binary cross entropy, and anything more than or equal to 3, you can use categorical cross entropy. So the training process is finished, and if you evaluate the model on test data, it returns the test accuracy of 64.79%. Actually, it looks better if you times 100. So 64. If you can do format like colon dot. If you want to print up to 3 floating point numbers, then dot 3f dot format, and like this. Now you can see around 64.79%, and let's add a percent here. And now let's see how much we can get if we load the best model. So the model save path is the path as designated here, which is saved in my drive, save the models, and models weight save model weights.h5. So let's check the accuracy. Enter. Takes a while. So by loading the best saved weights, we can get the much higher accuracy of 71.24%, which looks pretty good. So this is all for today's tutorial, and thanks for listening. Goodbye.